We're tackling a question that sounds kind of simple, but unpacks, well, basically everything. How can something like the wave function possibly explain these super complex things called four-dimensional wave propagation interactions? Our mission, really, is to take you on this conceptual ride. We'll trace how quantum theory grew up, from its early days in the 1920s right up to how we think about it now. We're going to figure out why those brilliant early ideas just weren't quite enough for a universe that also follows Einstein's relativity, and how that whole problem pushed physics towards quantum fields.
Yeah, it's a fascinating story, and it really starts with this fundamental clash. When quantum mechanics was first taking shape, especially with the Schrödinger equation, it almost immediately smacked right into special relativity. And this wasn't some small detail you could just patch up. It was deep, structural. It forced physicists to completely rethink how they described reality at the tiniest levels.
Okay, let's dig into that. So 1926, the Schrödinger equation arrives. A total game changer, right? It gave us the rules for non-relativistic quantum mechanics, how this thing called the wave function, psi, evolves over time. And it worked incredibly well, explaining atoms, how electrons move in materials, all that stuff. But like you said, it had this built-in problem. It just didn't mesh with special relativity.
Exactly. Special relativity had already shown, like 2 decades earlier, that space and time are woven together into space-time, a four-dimensional thing. And it demanded that physics laws look the same for everyone moving uniformly. Lorentz covariance, we call it. The Schrödinger equation. It's just not built that way. It's not Lorentz invariant. Einstein himself pointed out it uses ideas like absolute time and potential energy that just don't fit in a relativistic picture. Mathematically, you can see it clearly. It treats time differently from space. You've got one time derivative, but second derivatives for space. That asymmetry, it means the equation changes depending on how you're moving. Relativity says that can't happen. It kind of forces time to be this special universal parameter separate from space, which is fundamentally non-relativistic.
So this wave function, what did they actually think it was back then? It's this complex mathematical thing, but what's the physical meaning?
Well, the meaning really came from Max Born, also in 1926. The Born rule. He said, look, the probability of finding the particle somewhere, at some time that probability density is the square of the absolute value of the wave function. So it's not saying where the particle is, but where it's likely to be. It's fundamentally probabilistic.
Okay, probability.
Right. And for that to make sense, the total probability of finding it anywhere has to be 100%, or just 1. That's the normalization condition, over all space equals 1. And the key thing about Schrödinger's equation is that it preserves this. If you start normalized, you stay normalized. Probability is conserved. Particles don't just vanish or pop out of nowhere in this picture. There's even a continuity equation, EOJ plus EOJ, which shows this conservation is local. This idea of areos as conserved density was something they really wanted to keep when they tried to make things relativistic.
Okay, so the Schrödinger equation is powerful but flawed relativistically. What was the obvious next move? Like, how did they try to fix it first?
Well, the sort of first logical step was the Klein-Gordon equation. Klein-Gordon, Schrödinger himself, they all kind of landed on it independently. The derivation's pretty straightforward, actually. You take the relativistic energy-momentum relation, E bar TAU plus mAr T.
The famous one.
Right, and you just apply the standard quantum rules, replace energy E with its operator, amir E, and momentum pop with its operator.
The usual quantum substitution trick. Energy becomes the time derivative operator, momentum becomes the spatial derivative operator.
Got it. Exactly. You plug those operators into EPE plus an EU, do the math, and out pops the Klein-Gordon equation. You can write it really neatly using 4 vectors, and this U operator, the D'Alembertian, it looks like IA plus MCN.
And the big appeal initially was that it treated space and time the same way, both second derivatives. So, problem solved. Did everyone breathe a sigh of relief?
Well, the symmetry was nice, definitely. But the relief didn't last long at all. As soon as they tried to interpret E as a single particle's wave function, like Schrödinger's, huge problems cropped up. First big one, the probability density, it could be negative. Because the equation has 2 time derivatives, you can kind of set the initial conditions in a way that makes negatives.
Negative probability. That sounds impossible. Like, less than 0 chance.
Exactly. Physical absurdity. It just doesn't make sense. How can you have a negative chance of finding a particle? So that was a major crisis right there.
Okay, that's bad.
What else? The other killer was the negative energy solutions. Remember, E plus CC plus or GOCO. When you solve for E, you get E plus N minuses. plus and minus energies. In quantum mechanics, you can't just ignore those minus solutions. If they exist, particles could, in principle, cascade down into lower and lower infinitely negative energy states.
Meaning everything would just collapse.
Pretty much, all matter would be unstable, which, clearly isn't happening. And interestingly, these two problems, negative probability and negative energy, they're linked. The sign of the density actually tracks the sign of the energy E.
So it looked like a dead end. A mathematically nice equation, but physically nonsensical for a single particle. But then, Pauli and Weisskopf came along in 1934 with a completely different take.
Yes. It was really a radical reinterpretation. They basically said, hold on, what if A isn't a wave function for one particle at all? What if it's a field? And they suggested that the conserved quantity, the thing that could be negative, maybe it's not probability density, maybe it's electric charge density.
Charge can be positive or negative.
Exactly. So a density that isn't always positive is perfectly fine for charge. And this idea works beautifully for describing spin-zero particles, like the Higgs boson we found much later, or pi mesons. It was a massive conceptual leap. It took this failed wave equation and turned it into the foundation for describing certain types of particles within quantum field theory. It really pointed the way forward, showing that maybe fields were the key.
Okay, speaking of leaps, let's talk about Paul Dirac. 1928, he comes up with the Dirac equation. This thing didn't just fix problems, it made these incredible, totally unexpected predictions.
Dirac was really driven. He wanted an equation that was relativistic, obviously, but also first order in time, like Schrödinger's. He thought that was the key to getting a guaranteed positive probability density. But to make it work relativistically, it also had to be effectively first order in space. Now, how do you do that? It wasn't obvious at all. He ended up having to propose something pretty wild mathematically. The coefficients in his equation, they couldn't just be numbers. They had to be matrices. Specifically, 4x4 matrices that obeyed certain rules, anti-commutation relations, what we now call a Clifford algebra.
Whoa, okay, so the math itself forced a change.
Absolutely. And because of these matrices, the wave function couldn't be a simple number anymore. It had to have 4 components. A Dirac spinor, we call it. The equation itself looks deceptively simple in its compact form. OJUM MC. Where those goes are the Dirac matrices.
So what were the big wins? First, that positive probability density he was after.
Yes, success. The structure of his equation, with the spinors and matrices, automatically leads to a conserved quantity φ, which is basically A dagger times A. It's a sum of squares of the components' absolute values. So mathematically, it has to be positive or 0, never negative.
Okay, Klein-Gordon's biggest headache solved. What else?
This was maybe the most stunning part. Spin just emerged, naturally. Before Dirac, spin was just this property electrons seem to have, added by hand to make theories match experiments.
Right, it felt tacked on.
But Dirac's 4x4 matrices weren't put in there for spin. They were required for relativistic consistency. Yet when he looked at the non-relativistic limit of his equation, what popped out? The Pauli equation, which explicitly included spin. It meant spin wasn't some extra thing. It was an unavoidable consequence of making quantum mechanics relativistic for electrons. Someone famously said it was like pulling rabbits out of a hat, totally unexpected but undeniably there.
Incredible. But it didn't stop there, right? The negative energy problem was still lurking, wasn't it? His equation also had those solutions.
It did. Just like Klein-Gordon, you had positive energy solutions spin up and spin down, but also negative energy solutions spin up and down. But Dirac's interpretation of these was unbelievably bold.
The Dirac-C.
The Dirac-C. He proposed something truly profound. The vacuum, empty space, isn't empty at all. He said every single possible negative energy electron state is already filled.
With what?
With electrons. An infinite sea of them. But because they fill all the negative states and the Pauli exclusion principle stops any more from falling in, this sea is basically invisible, unobservable, like a perfectly smooth, full lake. But if you hit the sea with enough energy, say, from a photon, you could kick one of these negative energy electrons out of the sea up into a positive energy state. That electron becomes visible, real. And what's left behind in the sea? A hole. And Dirac showed this hole would behave exactly like a particle with the same mass as an electron, but with positive energy and, crucially, a positive charge.
An anti-electron, a positron.
Exactly. He predicted antimatter.
And then just a few years later, 1932, Carl Anderson actually found the positron in cosmic rays. That must have been mind-blowing confirmation.
Absolutely spectacular. A huge triumph.
Okay.
But, and there's often a but in physics, even this brilliant Dirac equation, when you really pushed on it as a single particle theory, showed cracks. that Dirac sea itself, it's inherently a many-body idea. You need infinite particles just to define the vacuum for one electron. Plus, the very idea of creating an electron-positron pair out of nothing, that shows particle number isn't conserved.
Ah, so you can't just talk about one particle anymore if pairs can pop into existence.
Precisely. In a relativistic world, you can't truly isolate one particle from the vacuum. The vacuum itself is dynamic, it's interacting. This tension, this inability to stick to a fixed number of particles was a huge pointer towards needing something even more fundamental. It screamed for quantum field theory.
Okay, so even Dirac's genius wasn't the final word for a single particle picture. What were the other big issues that showed relativistic quantum mechanics as it was then wasn't quite enough, beyond just the Dirac sea weirdness?
Well, the most unavoidable one was particle creation and annihilation. It just happens.
Yeah.
All the time. We see it constantly in experiments. Think about EMCR5. Mass is just a form of energy. And the Heisenberg uncertainty principle allows energy to fluctuate quite wildly over very short time spans. Put those together. If you have enough energy concentrated briefly, say more than twice the rest mass energy of an electron, to me on CR5, you can literally create an electron-positron pair out of that energy fluctuation. Like gamma ray photon comes in, poof, electron and positron fly out.
And the reverse, annihilation.
Yep. Electron meets positron, poof, they disappear into photons. These are not rare, exotic things. They're routinely observed. But the math of single-particle relativistic quantum mechanics, whether Klein-Gordon or Dirac, it just doesn't have the tools to describe particle numbers changing. It's built assuming the number of particles stays fixed. It's structurally incapable of handling creation and annihilation. So that was a huge practical limitation. But there was something even deeper, more conceptually damaging causality breakdown.
Causality, like cause and effect, nothing faster than light.
Exactly that, a cornerstone of relativity. Effects cannot precede their causes, and influences can't travel faster than light, so nothing should be able to happen between 2 points in spacetime if even light couldn't travel between them, what we call a space-like interval.
Okay, makes sense. So what went wrong in single-particle RQM?
Well, if you calculate the probability amplitude for a single particle, described by Klein-Gordon or Dirac, to get from point A to point B, this amplitude, the propagator, turns out to be non-zero even if A and B are space-like separated.
Wait, so it implies the particle could sort of instantaneously jump across a distance that light couldn't even cross in that time.
Yeah.
Faster than light influence.
That's what the math seemed to suggest for a single particle. It means if you detected a particle perfectly localized at point A, there's a non-zero chance of detecting it immediately at a faraway point B, faster than light could travel. This apparent causality seemed endemic to trying to force a single localized particle into a relativistic framework. It was fundamentally inconsistent.
Yikes. So how does reality fix this? Because clearly, things are causal.
This is where quantum field theory comes in and does something truly beautiful. It turns out the total amplitude isn't just the particle going from A to B, it's that amplitude plus the amplitude for its antiparticle to travel from B to A.
The antiparticle goes the other way.
Effectively, yes, in the calculation. And the magic is, when you add these two contributions together, the particle path and the antiparticle path for any space-like interval, they perfectly cancel each other out.
Wow. So causality is restored.
Exactly. Causality is perfectly preserved in QFT, but look what it took. It showed that antiparticles aren't just some quirky prediction of the Dirac equation. Their existence is absolutely essential, non-negotiable, to have a consistent causal relativistic theory. You need them to make the math work properly.
This really does sound like a complete paradigm shift, a total rethinking of what's fundamental.
Yeah.
This is quantum field theory, QFT.
It absolutely is. It's an ontological shift, really. QFT says the fundamental building blocks of the universe are not particles. They are continuous, fluid-like entities called quantum fields that permeate all of space-time. There's an electron field, a photon field for light, a Higgs field, fields for quarks, everything. These fields are the basic reality.
So what are particles then, like electrons and photons?
Particles get kind of demoted. An electron isn't a tiny ball bearing. It's a localized excitation, a quantized vibration, like a ripple or a wave packet in the underlying electron field. A photon is a quantized ripple in the photon field. All the properties we associate with a particle, its mass, its charge, its spin, are actually properties of the underlying field.
And the vacuum. The Dirac idea gets replaced.
Yeah, the vacuum in QFT isn't empty space, and it's not quite the filled Dirac either. It's the lowest energy state, the ground state of all these quantum fields combined. But it's far from inert. It's the seething, dynamic medium full of potential fluctuation. A dynamic, polarizable, many-body entity is a good way to put it.
And this field picture naturally handles things like particles being created or destroyed, right?
Yeah.
Because it's just ripples appearing or disappearing in the fields.
Exactly. It makes particle creation and annihilation completely natural. It's just fields interacting, exchanging energy, causing excitations, particles, to appear or disappear, like waves bumping into each other on a pond and creating new patterns. The framework is built for it.
How does the math work?
Yeah.
You hear about second quantization. Are we quantizing twice?
Yeah, it's a confusing name. It doesn't mean quantizing a second time. It really means applying the rules of quantum mechanics to the fields themselves, rather than just to particle positions and momenta like in the old QM. So the old wave function, x, gets promoted. It becomes a quantum field operator, let's call it x. It's not just a number anymore, it's an operator.
An operator? What does it operate on?
It operates on the state of the system, which now lives in a much bigger mathematical space called Fock space. Fock space is designed to handle systems with any number of particles, 0, 1, a million, whatever. The field operator x itself contains pieces that create particles at point x, creation operators, a, and pieces that destroy particles at point x, annihilation operators, a.
Ah, so the field itself has particle creation and destruction built right into its definition.
Precisely. And for fields corresponding to fermions, like electrons, these creation and annihilation operators have specific rules, anti-commutation relations, which automatically enforce the Pauli exclusion principle. It all fits together very elegantly.
So what happened to our old friend, the Schrödinger wave function? It's just gone, thrown out.
Not completely gone, no. But it's definitely fundamentally reinterpreted and demoted. It's no longer the star of the show. You can still recover something like the old wave function, but it's now understood as a specific kind of projection or matrix element of the field operator. Like, you can calculate the amplitude XPA, which represents the probability amplitude to find a single particle created from the vacuum state 0 by the field operator x with momentum p at position x.
So it's still a probability amplitude, but derives from something more fundamental.
Exactly. The fundamental thing is the state vector living in Fock space, and the field operators acting on it. The old wave function is just one particular way of extracting information about that state. It's a useful tool, but not the underlying reality itself.
So QFT gives us this amazing synthesis. The wave part of wave-particle duality is the fundamental continuous quantum field. And the particle part is the discrete quantized excitation of that field.
That's a perfect way to summarize it. The field is the wave, the particle is the quantum of excitation of that wave.
Okay, this is conceptually mind-bending. But QFT isn't just philosophy, right? It's how we actually calculate things in particle physics. How does it provide a practical framework for describing these interactions in 4 dimensions?
Right. It's incredibly powerful computationally. The starting point for almost any QFT calculation is the Lagrangian density, usually just called the Lagrangian, L. It's the single function that contains all the information about the fields and how they interact. The idea is the principle of least action. The fields evolve in such a way as to minimize the total action, which is the integral of this Lagrangian over all spacetime. And crucially, for relativity, the action must be a Lorentz scalar. It must look the same to all observers. A typical Lagrangian has a few standard parts. There are kinetic terms, usually involving derivatives of the fields, that describe how the fields propagate freely. There are mass terms, which give the fields excitations, the particles, their rest mass, and then the really interesting part, the interaction terms. These involve products of multiple fields, often 3 or 4 fields multiplied together at the same spacetime point. These terms describe all the ways particles can interact, scatter off each other, decay, be created, or annihilate. The strength of these interactions is governed by numbers called coupling constants.
Okay, so the Lagrangian sets the rules. How does QFT describe the actual propagation part? You mentioned the propagator before in fixing causality.
Yes, the propagator is key. In QFT, the propagator, often written xy, gives the probability amplitude for a quantum of the field, a particle to be created at space-time point y, travel through space-time, and then be annihilated at point x. It mathematically encodes how disturbances or excitations travel within the field. It's the fundamental way QFT describes propagation in 4 dimensions.
And calculating interactions, like two electrons bouncing off each other, involves these propagators and interaction terms. That sounds incredibly complicated.
It can be. But this is where Richard Feynman's stroke of genius comes in. Feynman diagrams from the late 1940s.
Ah, the little pictures. I've seen those. Lines and squiggles.
Exactly. Their genius is that they're not just cartoons. They are rigorous pictorial representations of specific mathematical terms that contribute to the overall interaction amplitude. There's a precise set of Feynman rules that tell you how to draw the diagrams allowed by your Lagrangian, and then how to translate each piece of the diagram back into a mathematical formula.
So what do the pieces mean?
Okay, so the lines coming in from the outside or going out, those represent the real incoming and outgoing particles that you could actually detect in an experiment. The lines inside the diagram connecting different points, those represent the propagators. They show particles traveling between interaction points. These internal particles are called virtual particles.
Virtual, meaning not quite real.
Yeah, they don't obey the usual E-uval, A-clo, E-t scilab plus M serial relation. They're off-shell. They represent temporary fluctuations of the field that mediate the interaction. They exist only within the confines of the quantum process described by the diagram. They are the direct graphical picture of that 4-dimensional wave propagation we were talking about.
Yeah.
And the points where the lines meet, those are the vertices. Each vertex corresponds directly to an interaction term in the Lagrangian. Its mathematical value is proportional to the coupling constant for that interaction.
So to calculate, say, electron scattering, you draw all the possible ways they could interact using these lines and vertices.
Precisely. You draw all possible diagrams connecting the initial electrons to the final electrons. Maybe they exchange one virtual photon, maybe two. Maybe a virtual photon creates a temporary electron-positron pair, which then annihilates back into a photon. You have to consider all possibilities allowed by the rules. Then you translate each diagram into math using the Feynman rules, and you sum up the contributions from all the diagrams. This sum over histories, as Feynman called it, gives you the total probability amplitude for the process. Each diagram is literally a map of one possible history of interaction and propagation through space-time.
Wow, so let's try and wrap this incredible journey up. We started with Schrödinger's wave function, saw its relativistic limitations, went through the attempts of Klein-Gordon and Dirac, which solved some problems but raised others, like negative energy and antimatter, and ultimately arrived at quantum field theory. It really has been a century of, well, intense intellectual struggle and amazing discovery. And go back to our original question, how does the wave function account for 4-dimensional wave propagation interactions? The answer seems to be, it doesn't, not directly. The whole picture had to change. It required this complete re-envisioning of reality.
That's exactly right. QFT fundamentally redefined the key concepts. The wave function, it's no longer the fundamental description. It's replaced by the quantum field operator X, which creates and destroys particles. The state of the system is an abstract thing in Fock space. The old is just one way to look at it. Wave propagation. It's not about A changing shape. It's described precisely by the propagator, the amplitude for a field excitation to travel between space-time points X and Y, and interactions. They're not potentials acting on A. They are local couplings between different quantum fields written down in the Lagrangian and visualized and calculated using Feynman diagrams, vertices for the couplings, internal lines for the propagation of virtual particles mediating the forces.
So QFT is really the only game in town if you want to consistently describe particles, relativity, creation, annihilation, and causality all together. It managed it by basically throwing out the classical idea of a particle as fundamental and rebuilding everything on the foundation of fields. The old wave function finds its place, but it's redefined, demoted. It's a tool to interpret the behavior of the truly fundamental things, the quantum fields. And maybe a final thought to leave you with. Remember that vacuum state in QFT, the lowest energy state of all fields. It's not truly empty, it's fizzing with constant activity. Virtual particle pairs are popping into and out of existence all the time. This quantum foam isn't just theoretical speculation, its effects are measurable. They subtly shift the energy levels in atoms, that's the Lamb shift. They even create a tiny real force between uncharged metal plates held very close together, the Casimir effect. So that seemingly empty space around you is actually a seething cauldron of quantum reality, constantly influencing the world we see. Something to think about.